So, hello everyone. So, let's get started with the next step. In the previous videos, you had seen solving load flow using two bus system, but now we'll go with a slightly more bigger and complicated network of three bus system. So, uh, when I say bigger and complicated, that is from the with reference to our human hand calculations. So, typical size of a system would be anywhere like 500 buses to or even 1000 buses. So these are, of course, they are run by computers. So, but actually writing down the equations and solving by simple equations, hand calculations. Of course, we still use computer for even this case also. But then if you write down the equations, it is a once in a lifetime learning experience. So I encourage everyone to see this video and then practice the equations which I'm writing here. I'm just writing this is must for every power engineer uh, to write down the equations for a Newton-Raphson three bus system. Three bus, three unknowns. So this is when I say this is must, but then it's only a once in a lifetime activity. So once you do it, you understand it, then you don't have to do it again. Of course, my case is different. I keep teaching this subject every year, so I'll have to repeat it. But then uh, this is a once in a lifetime activity. So so treat it that way. Treat it like a special moment in your life. So and let's take it up. So I'll draw the circuit. So a three bus system will have a three buses. So one, two, and let's write it here three. So or I would also like to have connection between one and three also. So this is bus one, bus two, and bus three. So bus one is connected to bus two via a transmission line whose impedance is zero point 0.1 per unit. So all the values impedances are in per unit. Then bus 2 is connected to bus 3 and bus 1 is also connected to bus 3. So let's say this is J zero point 0.2 per unit and let's say this is J 0.25 per unit. So I'm giving the impedances of the lines in per unit. Now I can define generators and loads. So the problem is if I define bus 2 as a load bus and bus 3 also as a load bus, then I'll get four unknowns. So then I have to write four equations, which will take even more time. So but to make the concept understandable and also to keep the problem size smaller, I'll consider one of the buses as my generator bus. So let's say this is a generator bus and bus 1 also is a generator bus. So I'm generating power at bus 1 and at bus 3. So for simplicity, I'm not assuming any impedance of the generators here. So because that is not the point we are discussing. We want to study Newton-Raphson load flow. Okay. Now, what are the values? By the way, I have drawn a load here. I'll define some load, but then that I will define slightly lesser than the generator, so it will not be a problem. So let me define the loads here. So P3, PL3, so or I'll write it SL3, the complex load is nothing but 0.7 plus J 0.4 per unit. So 0.7 per unit of active power demand is there, 0.4 per unit of reactive power demand is there. Whereas SG3, so G represents generator at bus 3, the complex power generation. So by the way, I cannot define SG3 because whenever there is a generator, I can only define how much is the active power I am generating and then what is the voltage value. All right, so let's write the active power that I'm generating. Let's say 1.3 per unit is the active power generated. That is Pg3. What about Qg3? That it generates, of course, it generates some reactive power. Right now, I don't know how much it is. But then I know the magnitude of V3. I may not know the angle of V3. The magnitude of V3, let's say it is 1.01 per unit. So 1% slightly higher voltage than the rated voltage I'm generating. So of course there is nothing special about 1.01. It could as well be 1.02 or 1.04 or even sometimes 0.98 or whatever. So this is the data at the bus 3. Now look at bus 2. So there is no generation here. Bus 2 is purely a load bus. So V2 and delta 2 both are unknowns. Two unknowns are there. Here delta 3 is unknown. So P, here I'll write the complex demand SL3, sorry, SL2. Let's say the load here is 0.9 per unit, 0.9 plus J 0.5 per unit. So this much is the power demand here. Active power is 0.9 per unit and reactive power is 0.5 per unit. What about at bus 1? So this is a slack bus, which automatically means I know V1 and delta 1. So V1 delta 1 is known, and let's assume V1 is 1.0, delta 1 is 0 degrees. So this is again I can define 1.05 or 0.98 or whatever. So here this is the data given. You know V1 and you know delta 1. But what about power generated at this generator? So it is actually not required for solving the problem, because the slack bus role is to generate the power whatever balance is required. So for example, here the generation, here the demand is 0.7, here the demand is 0.9. So 1.6 is the power demand, whereas power generation is only 1.3. So the balance 0.3 power has to come from the slack bus. Not only that, if there are any losses in the network, that losses also have to come from slack bus. But then if you further notice, I have defined only the impedance in the form of a reactance only. I did not give the resistance. So sometimes 0.05 plus J 0.1 per unit, like that the data will be given. Then it is a there is some losses in the line 1 2 also. But for the time being, for this problem, because I want to write down the equations, I want to learn the concept, so I'm ignoring the resistance of this line. So this is the data given to you. So given data. On a 3-bus system. So what is our objective? So our objective, determine unknowns, or we'll say unknown states of system using NR method. So what do we mean by states? States are nothing but the voltage magnitudes and voltage angles of all the three. So there are 3 buses, so I have 6 states, V1, V2, V3, delta 1, delta 2, delta 3. But some states are known, some states are unknown. So let's begin our solution. So for the solution, let's do this. I'll begin by listing out known states and unknown states. So known states are, so I know delta 1, I know V1, and I know V3. So why I know delta 1 and V1? Because it is a slack bus. And why I know V3? Because it is a generator bus. What I don't know is delta 2, delta 3, and V2. So you notice that the ordering, first I'm writing down the deltas followed by V's in the unknowns. So this ordering is very important. Once you write this ordering, you don't know delta 2, you don't know delta 3, and you don't know V2. So total there are 6 states. V1 delta 1, V2 delta. So V1 delta 1, V2 delta 2, V3 delta 3 are the 6 states. So whatever is known, V1 is known, delta 1 is known, V3 is known. So this three other three don't, you don't know. So that's what I have listed down here. Now corresponding equations. Corresponding power flow equations. So because delta 2, delta 3, V2 are unknown, corresponding to delta 2 I have equation for P2, corresponding to delta 3 I have equation for P3, and corresponding to V2 I have equation for Q2. So for delta P is the corresponding equation, for again delta 3 P is the, and then for V Q is the corresponding equation. So that is step 1. So I have identified these 3. So now come to step 2. Step 2 is write down the equations. Or even before I write down the equations, blindly let's build a Y bus. These are parallel steps, so you can do anytime. So Y bus obviously will have a, I'll very short network I'll draw. See, the line between 1 to 2 is J 0.1. So if I invert this, I'll get the admittance Y12 is minus J10. Similarly here, Y23, I'll get minus J5 because 1 divided by J 0.2 is this. And 1 divided by J 0.24 is Y13, that is minus J4. So minus J10, minus J5 and minus J4. 1, 2 and 3. So from this information I can build the Y bus. So what is my Y bus? So first I'll fill the off diagonal elements. So my off diagonal elements are, so this is line between 1 and 2. So this is J10. I have to remove the minus sign. Line between 1 and 3, this is J4. So this will be J10 and J4. Then the lines connecting 2 and 3 is J5. So it will become J5 like this. And then addition of these two is J14. So minus J14. There are no impedances connecting to the ground. If there are any impedances connecting to the ground, they should be added to this. You all know this procedure, I am assuming. So minus J15 and this is minus J9. So this is my Y bus. Now Y bus I can separately write as the magnitude of Y bus elements and the theta of Y bus elements. So if I just write the magnitude without worrying about the plus minus, so it is 14, 10, 4 and this is 10, 15, 5 and this is 4, 5, 9. So I'm not worrying about the sign. And the theta. So theta, that is the angle of each element of this. So it will be pi by 2 multiplied by minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1. So this is my thetas. So for example, if you take this element y1, 3, the first row, third element, its magnitude is 4 and its angle is pi by 2. Because pi by 2 is common multiplying with everyone. So 4 at angle of 5. So this pi by 2 is coming because we are ignoring the resistance of the line. But if there is a resistance of the line, then this angle will be slightly less than 90 degrees. Alright, we finished our step 2. So let's go to step 3. So what is our step 3? So let's write the functions. So the functions, what I want to write is P2, P3 and Q2. So the function of P2, function of Q2 and the function of, sorry, the ordering I should always maintain that, and the function of Q2. I know this, all these values are zeros. So here we use the general general power flow equations. So what is the general power flow equations? Pk equal to Qk equal to. This is nothing but summation of I equal to 1 to 3 Yki Vi Vk cos of theta Ki plus delta I minus delta K. Similarly, Qk is minus of I equal to 1 to, this is not 3, this is n, because it's a general n bus system. Exactly the same thing, just instead of cos, I'll get sine. So using these two, I'll write the three functions here. So these are my general equations. In fact, let me move it down. These things I'll move it down. And I might also require more space for this. So let's try to adjust that. All right. So general power flow equations. Now, what is FP2? So what is FP2? So from this, it's a summation of three terms. Okay. So first term, second term, and third term, I'll write it here. First term is, so how do I write it in the form of 0? So if I put 0 here, if I put 0 here, then minus pk will come here. If I put 0 here, minus qk will come here. Just generalized equations. So let's write that. So this will be y21 v1 v2 cos of theta 21 plus delta 1 minus delta 2. So this is the first term. The second term will be y22 v2 v2 cos of theta 22. So delta 2 minus delta 2, it will become 0, so I am not writing that. In fact, this is v2 square. And the third term will be y23 v3 v2 then cos of theta 23 plus delta 3 minus delta 2. So this is the first expression. Of course, minus p2 is there to make it equal to 0. So this is my first equation. So let's continue. Let's write down the second equation. That is FP3. So FP3, I'll just look at the generalized equation above and then do that. Or in the place of 2, I'll just replace it with 3. So let's do it. Y31 V3 V1 V3. Then I have cos of theta 31 plus delta 1 minus delta 3. So this is first term plus y32 v2 v3 cos of theta 32 plus delta 2 minus delta 3. This is second term. And the last term is y33 v3 v3 or v3 square, I can put it, and then cos of theta 33. So delta 3 minus delta 3 I'm just ignoring because it is 0. So this is also done. Now let's write one more equation, that is FQ3. So FQ3 is the third function. The value is 0 anyway, I know that. So which is nothing but So minus yki vi vk. So sorry, this is q2 because q2 is known. So this is minus y21 v1 v2. Here I'll get sine of theta 21 plus delta 1 minus delta 2. Then the second term will also be minus y22 v2 square. So cos of theta 22. So these two terms will cancel out. Then again minus 2 3 v3 v2. Sorry, this is sine. Then again sine of theta 23 plus theta 2 minus theta 3 minus delta 2. Sorry. So this is my third equation. So we had three equations ready now. The next step is to find the Jacobian matrix. That means I have to differentiate these three equations with respect to three variables. So let me write down the Jacobian matrix. This is the biggest, so that's why I'm saying it is a once in a lifetime experience. So the Jacobian matrix will have 9 elements. So I have 3 functions and 3 unknowns, so I have get 9 combinations. So the function is function of p2, function of p3 and function of q3, and the unknown variables are delta 2, delta 3 and sorry, this is q2 and this is v2. So here I'll get partial differentiation of function p2, that is the first function. So partial differentiation of function p2, partial differentiation of function p2 with respect to the first variable delta 2, with respect to the second variable delta 3, with respect to the third variable v2. So like this. Similarly here, partial differentiation of function p3 with respect to first variable, with respect to second variable, with respect to third variable. Third variable is sorry, v2. Similarly here, partial differentiation of third function, function of q2 divided by first variable delta 2, partial differentiation of third function, that is function of q2 divided by second variable, that is delta 3, partial differentiation of third function q2 divided by third variable v2. So these are the 9 elements of the Jacobian matrix. One by one we will have to solve it. So I've been doing this video for a few minutes now. So let me take a couple of minutes break, and after the break I will continue this. So let me quickly review. We wanted to do Newton-Raphson load flow for a 3-bus system. This is a must for every power engineer to write down the equations for 3-bus and 3 unknown systems. So if you have not done it anytime in your life, please do it at least once. I have taken a sample 3-bus system with some sample values. So then coming down, the objective is to determine the unknown states. The objective is to find out the values of delta 2, delta 3 and v2. Corresponding to delta 2, delta 3, v2, p2, p3, q2 are the power flow equations I need to solve. And before that, we are just building a y bus and then separating it into the magnitudes and thetas. And then going down, I am writing the generalized functions. And then from the generalized functions, I will get the first function. So let's denote it as function 1, function 2 and function 3. So these 3 functions I will differentiate it one by one and then I will get the elements of J matrix. So this I will do it in the continuation video. So let's take a break. I'm a little bit tired. I'll have some water. Bye.